Hi, my name is Ziwei Ji, and I'm going to present our work. Gradient descent follows the regularization path for general losses. This is a joint work with Miroslav Dudik, Schapire, and Matus Telgarsky. First, let me introduce the background of our problem. A central problem in machine learning is to avoid overfitting, and there are usually two ways to do that. The first one is to add an explicit regularizer to the risk function, such as the L1 regularizer, L2 regularizer, and so on. The second option is to use some implicit regularization properties of the training algorithms, including coordinate descent or ADA boost, and gradient descent, and so on. It can be observed in practice that such algorithms can find solutions that have both a small training error and a small test error. Moreover, if we use an exponentially tilted loss function, such as the exponential loss or the logistic loss, then these two kinds of regularization are closely related. For example, if we use the L1 regularization, then as we decrease the strength of the regularizer to 0, the regularized solution will asymptotically maximize the L1 margin. And also, if we run coordinate descent for a long enough time, it will also maximize the L1 margin. Similarly, both the L2 regularization and gradient descent can maximize the L2 margin. This raises the key question studied in this paper. What about general classification losses? Is there still a relationship between these two kinds of regularization? Here is some empirical observation. We can start linear classifiers over a synthetic, linearly separable dataset. The blue points represent the positive examples, and the red points represent the negative examples. This horizontal line represents the maximum margin direction. The solid lines represent the gradient descent traits, with different colors indicating different loss functions. The dotted lines represent the path of the regularized solutions as we decrease the strength of the regularizer. So far, all look similar. The gradient descent part and the regularization part are close to each other for different loss functions. So can we expect that the gradient descent path will keep following the regularization path, and will the gradient descent path eventually point towards the maximum margin direction? The answer is that it depends on which loss function we use. If we run the gradient descent for a long enough time, then as we can see here, if we use the exponential loss function, then both the gradient descent path and the regularization path will converge to the maximum margin direction. However, this is not true for the other loss functions, such as the 1 plus d to the minus 1 or 1 plus d to the minus 2. However, even for these two losses, the gradient descent path and the regularization path always track each other and converge to the same direction. And this is what we prove in this paper, that for any convex strictly decreasing loss function, the gradient descent path and the regularization path always track each other. Next, I'm going to introduce some notation and formally state and discuss our result. We consider a binary classification problem with features I and labels features xi and labels yi. We consider linear classifiers with the standard empirical risk function, and here L denotes the loss function. Next, given a norm constraint B, the regularized solution W bar B is defined as the minimizer of the empirical risk function within the L2 bar of radius B. This definition is slightly different from the standard definition of the regularized solution as the minimizer of the sum of the risk and the sum L2 regularizer. However, these two definitions give the same regularization path, and therefore it does not affect our result. And for simplicity, in this paper, we just use the definition given here. We also consider the standard gradient descent with a constant step size eta. Here is our main result. If we assume that the loss function is convex and strictly decreasing to 0, and if the empirical risk function R doesn't attain its infimum, then we can show that the limit of Wt over the norm of Wt, in other words, the limit of the direction of Wt, is equal to the limit of W bar B over B whenever other limit exists, as long as the step plus eta is positive and small enough. Let me explain this result a little bit. Under the given conditions, we can prove that Wt will go to the infinity, meaning that its norm will go to the infinity. And similarly, we can prove that the norm of W bar B is equal to B, and therefore they also go to the infinity. So Wt and W bar B do not converge to a finite point, and that's why we have to study their directions. And even if we only look at their directions, it turns out that Wt and W bar B may not converge to any direction. We give such an example in our paper where we can construct a pathological convex strictly decreasing loss for which Wt and W bar B do not converge to any direction. On the other hand, our main theorem states that as long as one of Wt and W bar B converges to some direction, the other one also converges to the same direction. It is also natural to ask, when does assumption 3 hold? When does the empirical risk R not attain its infimum? This is true if the dataset is linearly separable, and which is often assumed in prior work. However, we don't actually need to assume separability. It can be shown that any dataset can be uniquely decomposed into a non-separable part and a separable part, and assumption 3 holds as long as the separable part is non-empty. We will discuss the details about this decomposition later. The next comment is on different loss functions. It is shown in prior work that if we use an exponentially tailed loss, such as the exponential loss e to the minus d, or the logistic loss log 1 plus e to the minus d, then both gradient descent and the regular solutions will converge to the maximum margin direction. The prior proof ideas are based on some special properties of the exponential function and the maximum margin direction. We cannot use such ideas in our paper because we are considering an arbitrary convex strictly decreasing loss, and in this setting, the margin may not be maximized. Therefore, we have to use some new technique, and specifically, we use a perceptron-style analysis. Finally, I want to discuss how to apply our main theorem. It is interesting to study the implicit bias of gradient descent, meaning that the limit of the direction of Wt. However, this is usually hard to analyze. On the other hand, the implicit bias of the regularized solutions, meaning the limit of W bar B over B, is usually much easier to analyze because it doesn't depend on any algorithm. It doesn't depend on the training algorithm. Therefore, to determine the implicit bias of gradient descent, we can just first derive the algorithm-independent bias, the limit of W bar B over B, and then invoke our main theorem. Okay, so here are the comments on the main result. And next, I'm going to discuss more details about the difference between loss functions and this decomposition of an arbitrary dataset into two parts. Okay, so here, for simplicity, we assume that the dataset is linearly separable. And we first consider exponentially tailed losses, such as the exponential loss or the logistic loss. As mentioned before in prior work, it is proved that both Wt and W bar B converge to the L2 maximum margin direction. And also, as mentioned before, it is usually hard. It is kind of hard to prove that the gradient descent iterate Wt converges to the maximum margin direction. But on the other hand, it is much easier to show that W bar B over B converges to the maximum margin direction. The intuition is that as B becomes large enough, the empirical risk kind of only depends on the support vectors, and because W bar B has to minimize the empirical risk within a certain L2 board, it has to asymptotically maximize the margin. And after we proved the convergence of W bar B over B, we can just invoke our main theorem and reprove the fact that Wt also converges to the maximum margin direction. We can also consider other loss functions such as the polynomially tilde losses, including 1 plus d to the minus k. In this case, we can also show that the limit of w bar b over b exists, and therefore by our result, the gradient descent iterate wt also converges to the same direction. However, in this setting, the margin may not be maximized. Specifically, we can show that for any n, there exists a dataset with n training examples where the maximum margin is always at least 0.1, but if we run gradient descent with the loss function 1 plus d to the minus k, then the final margin we get is only of order n to the minus 1 over k plus 1. So this result means that indeed we cannot use the prior proof ideas based on the maximum margin direction, and we have to use a new proof technique. It also sort of gives a justification for the exponentially tilde losses because they can always maximize the margin. On the other hand, this dataset given here, on which the polynomially tilde losses have a bad margin, is kind of pathological, and it may not actually appear in practice. Therefore, it is an interesting open problem to conduct a thorough comparison between the exponentially tilde losses and the polynomially tilde losses, and perhaps other loss functions. Next, I want to discuss the decomposition of a dataset and then use it to give a detailed characterization of the gradient descent iterates and the regularized solutions. We need a structural result from one of our prior work. Given any training dataset with n training examples, there exists a unique subset S of 1 to n and a vector u such that you can classify any data examples whose indices are in S with a positive margin, and u is orthogonal to any features whose indices are outside of S. Moreover, the empirical risk over the complement of S is strongly convex. With such a decomposition result, we can give a final characterization of the gradient descent iterate Wt and the regularized solution W bar B. First, if S is non-empty, then the empirical risk function R doesn't attain its infimum, and therefore all the conditions of our main result hold, and we can prove that the limit of Wt over the norm of Wt is equal to the limit of W bar B over B whenever other limit exists. On the other hand, we can also consider the space spanned by the features whose indices are not in S. This space is orthogonal to the limit of the direction which we obtained in the first part, and on this space we can prove that both Wt and W bar B converge to the unique minimizer of the empirical risk over the complement of S. Specifically, if S is empty, then the whole empirical risk function R is strongly convex, and in this setting, both Wt and W bar B will converge to a finite minimizer. Okay, so in summary, in this paper, we proved that for any convex strictly decreasing loss, gradient descent follows the regularization path. This is all for my talk. Thanks for listening, and I'm happy to take any question.